space, which is a topic of this conference. And we have extensive cooperation in the Asia-Pacific region, with ISRO, of course, but also with China, with Japan, and South Korea. So the purpose of my talk is to give a bit of a flavor of the EUMETSAT program, but more specifically to address possible cooperation models that we have experienced already and which could be relevant for future cooperation on climate and on the monitoring of carbon. So, as I told you, our job is about weather and climate from space. We are not a development agency, we are an operational agency, which means we rely on development agencies to develop our spacecraft and instruments to fulfill our requirements. But as you see, this is our convention, this is the official mandate of EUMETSAT. So in short, European operational satellite system for meteorology, but also contribution to monitoring climate and climate change. And the rationale is that you need much more than observation of the atmosphere for advanced meteorology, and there are obvious synergies. So I will go fast on that one. The message is that we commit to multi-satellite programs for decades. What you see on the top is METEOSAT, our geostationary program. We are in the second generation. We will enter soon in the third generation with advanced capabilities. We are also operating polar orbiting spacecraft on the mid-morning orbit, and again, we are in our first generation. I will go in the next second generation in the 2020 timeframe. We are also partnering with NOAA, NASA, and CNES on the JSON high precision altimetry missions. And you have heard already that JSON 3 was launched in January, and we plan to continue together with the EU. So ocean and climate is an important element of our missions. And last but not least, we play a role in the EU Copernicus program, meaning that we have delegated responsibility to operate 4 of the 6 Sentinel missions. Not surprisingly, those dedicated to the observation of the ocean and the atmospheric composition. So this is the current missions we have in orbit. We have 4 METEOSAT second generation around 0 degrees. Interestingly, we have 1 satellite of our first generation still operating over the Indian Ocean, and we plan to send a second generation satellite over the Indian Ocean next year in cooperation with ISRO and other agencies. We have 2 polar orbiting satellites in orbit, and today we share 2 JSON missions with CNES, NOAA, and NASA. So as I told you, we are finishing to deploy the current generation of spacecraft. The 4 METEOSAT second generation spacecraft are in orbit. It means we have a safe ground to prepare the transition for the third generation program, which is a very challenging program. And we plan to launch the last METEOSAT Pro satellites in the mid-morning polar orbit in October 18. A few words about the new satellite programs, which were approved last year, at least for the low Earth orbit satellites. So, as I told you, we have a solid ground to deliver observation until 2040, which is very essential for weather, but also for climate. So MTG will be a twin satellite program, 2 satellites operated simultaneously in orbit. The first one will have 16 channels instead of 12. We'll have lightning imager. We'll have 2.5 to 10 minute repeat cycles and higher resolution. So we will do much better than what we do today. The second one is a sounding mission, hyperspectral sounding mission, providing vertical soundings of moisture and temperature and some trace cases every 30 minutes over Europe, and probably every 1 hour on the full disk. So it's a very new capability which we believe will revolutionize regional numerical weather prediction. On the polar orbit, it's the same. We will do everything better than we do today with the current METOP satellites. But on top of that, we have new instruments. We'll have microwave imagery for precipitation. We'll have a nice cloud imager observing at very high frequency, around 600 gigahertz. And we will have a polarimetry imager. Copernicus, I told you, so we will operate this mission. I use the word hosted mission because in the case of Sentinel-4 and Sentinel-5, which are dedicated to observation of the atmospheric composition, we will host the mission as part of our system, so additional instruments on our spacecraft, but also the ground segment the processing will be integrated in our full system. So I'm coming now to internal cooperation. The first thing I have to say is that EUMETSAT is international cooperation. It's an interesting model. We have 30 member states, and it's much more than the number of spacefaring nations in Europe, as you realize, which means there is another interest than just building hardware. It's really the benefit of the data, which is a driving factor for all these countries to pool their resources into EUMETSAT. I will not address benefit, but I can give you a figure. Weather forecast in Europe, 60 billion euros per year, out of which you can attribute 6 billion to one METOP satellite. So benefit to cost ratio, 20. This is the reason why we got 4 new member states in such a difficult economic situation in the last 3 years. So cooperation, we are cooperation, but we are also very much interested in cooperation with other agencies across the world and also, of course, in the Asia-Pacific region. We participate in the multilateral framework, but we also have bilateral cooperation with partner agencies. First, for development purposes. I told you with ESA, CNES, DLR, but it's more European business to make sure we have the most advanced sensor to fulfill our requirements. But we cooperate also with others in various models to establish synergies with our own mission and to reach a broader user community. For instance, our data flow to India, to Japan, to China through various communication means as per data exchange agreements. So, which model? We have experience of a number of cooperation models. The first one, which is quite obvious, is a joint cooperative mission, and the case this is JSON, together with the US and France, soon ESA. Another model we have, which is extremely interesting, is autonomous contributions to a shared integrated system. And this is what we do with NOAA. We share orbits, we fulfill commonly agreed requirements, and we have cross-ground support. And the system is really operated as an integrated system. We had what I call hosted payload or missions. I should use hosted missions because hosted payload may have a different meaning in the US in particular. But we host the Argos terminal on our polar orbiting satellites because we have great interest in the collection of ocean data. And Argos is a great system for that. And as I told you already, we host missions for atmospheric composition monitoring as part of MTG and EPSSG. We have also other models, cooperations on ground in operations, so we can provide TT&C support, data acquisition support, data circulation. We can process data, co-process data among partners. We have cross-calibration, validation. We have data exchange and redistribution to respective user communities. And last but not least, we have cooperation, science, and user support programs. So, an example, JSON as a cooperative mission. You see a lot of logos. It may look more and more complexity. To some extent, it's true, but it also shows that through these joint missions, we are able to achieve the transition from research to operational missions, which I believe is extremely relevant on what we may do in the future for missions dedicated to monitoring carbon emissions. The joint integrated system, you see these 2 orbits, and you see we have just time for another 20 years. But we have 2 orbits, but very soon our Chinese colleagues will go to a third complementary orbit, which was announced at the WMO Congress, which is a historical decision, because we'll have 3 complementary orbits and benefits for the full planet, for weather forecast and climate monitoring. So this type of cooperation, the equation is 1 + 1 is more than 2. What you see on this graph is the impact of losing one spacecraft, the impact on weather prediction. You see it's for European model, ECMWF. If we lose METOP, we lose performance. If we lose NOAA satellite, we lose performance. But if we lose 2, we lose much more than the sum of the 2 losses. So it's a way to show that the benefit of cooperation is tangible and measurable. Hosted missions. This is Sentinel-5. Sentinel-5 is a UV and near-infrared sounder, so we will observe a number of trace gases in the atmosphere. With the SENG, which is developed by CNES, we will observe another part of the spectrum and access other trace gases. So the synergy is obvious, and if you add that together with that, we have imagers to know where the clouds are. It's a real, true, impressive synergy that we are expecting on METOP-SG satellites. Cooperation on ground, and of course I started with ISRO. For SARAL, you have heard it's a joint mission between ISRO and CNES. We host European capability for near real-time processing and distribution to products of users. And we do the same for Megatropic under a tripartite agreement with ISRO and CNES. So it's an example. If I take China, we have recently agreed that the data of our respective satellite can be broadcast to network of ground station, and then we collect the data and deliver regional service. The value is that data can be available within 15 to 30 minutes from sensing, which again is critical for regional models. Cooperation on processing. This is what we had agreement with NASA, with ISRO, with CSOA in China to process and redistribute data. And recently we have QuickScat, which has a very interesting orbit, as Charlie Bolden has explained, and I can confirm that. We also redistribute data from JPM and GCOM W from JAXA and NASA. So another important cooperation is cross-calibration. This is done multilaterally, but with bilateral cooperation on some aspects. And the net result is that platforms and services allowing to compare, evaluate, cross-calibrate measurements. For instance, infrared imagery from geostationary orbit is today cross-calibrated with YASI, which is a very stable instrument. So this is another form of cooperation. And it's very valuable for climate. You see here that cross-calibrating everything, we are able to combine data from the geostationary ring into global products. This is albedo, and from Japan, China, and this is part of a multilateral cooperation project called SCOPE-CM. Cooperation science. Here you have CO2 and CH4 in the mid-atmosphere. It's not emission, it's not close enough to the ground, but it's important to see what parts of these trace gases, these greenhouse gases remains in the middle atmosphere. We validate at stations, and this is we have monthly products, and this is a research and user program which is supported by ourselves and by CNES. So now internal coordination, which certainly shall not be neglected, and you will see why. A first form of this coordination is a coordinated definition of respective missions, observing capabilities, orbits, and you will see for meteorology there are frameworks within WMO, but we have also coordinated operations and planning of respective missions. So I will give you a few examples. So this is not really the slide I would like to show, but this is the current situation of the WMO, the World Meteorological Organization Global Observing System. The one I wanted to show you, which I could not find, is a target, because it's very important This is a picture of today. What matters is the target for tomorrow. And we have a GOS 2025 vision established by the WMO, which sets the objectives for 2025. And this is where the Chinese will have a major contribution, because this scheme includes 3 orbits. And the 3 orbits now, from 2018, I understand, will be delivered by the FY3 family of satellites, which will bring an enormous benefit to the world community. So coordinated operations, this is the Indian Ocean, and this is the work of the coordination group of meteorological satellites, where we have agreed to have a more resilient system over the Indian Ocean, combining the assets of China, Israel, Russia, and Japan. And you see the different coverage. And the beauty of the cooperation with ISRO in particular is that we will have 1 METEOSAT at 0 degrees, 1 METEOSAT at 41.5 degrees, and then INSAT 3D around 80 degrees. So you see, and we have overlap, we can cross-calibrate, we can compare products. It's really a great opportunity, and I hope EUMETSAT will confirm in June that we'll move METEOSAT 8 to 41.5 degrees east. Other examples of coordination, virtual constellations, ocean surface topography. I talked about JSON, but JSON is a reference mission used to cross-calibrate others, and we need a combination of mission to sample the ocean variability and climate. And we have an international science team also to guide us on the best possible synergy and the design of this. And here you see, I could have others, but you have what you see is a sampling of the ocean by JSON every 10 days in white, and you have Sentinel 3 every 27 days, so but with and here you have on the right also Sarah-Laltica. We could have also HY2 from Chinese, with also a very different orbit. So combining this, we sample the ocean as good as possible. We can observe the rapid movement in the tropics, the slower movement in the mid-latitudes, and we have definitely a system based on international coordination. And the benefit is this. Of course, it's a bit European-centered, but I could have shown you every part of the world, including the Pacific. We get better information. You see the pulse of the planet here, the pulse of the ocean, but the result is that we have information services which are much better because they are fed with more and well-coordinated data sources. This one also I like very much. It's the Sandy hurricane which hit the US during the presidential election, and you can see it observed at different times by different scatterometer missions, because METOP, because OceanSat 2, because ICE-WAY 2A have different and complementary orbits. So this shows the value of coordinating orbit. It's true for scatterometry, it's true for a lot of things, and it will be true for carbon, I'm sure. This virtual constellation has the merits because we review the situation from time to time to see where we have gaps. And we do have gaps for precipitation. Precipitation are terribly difficult to sample in space and time. We have a remarkable mission, which is GPM, which is also a constellation concept. But you see here we have a hole, and we do expect, we hope that Japan will be able to approve a follow-up to the GCOM 21 mission. And the more so because the MSP 29 and 19, unfortunately, has been probably lost last week. So here I quote our climate symposium in 2014, where all the agencies were there to talk about space observations and climate monitoring. And I quote the conclusion of the science panel, which said, yes, we need to combine multi-satellite operational programs and research missions. This is essential. This is also one reason we are here. We need to learn from the research mission to plan for the future. We need also to take into account the operational systems to design the research mission when combination of observation is required to fulfill scientific requirement. And also, it's recognized that some research missions continue. And I know some continue. And I know Grace follow-on is approved on the NASA side. It's a great mission. The situation may be a bit less clear on what comes after the global precipitation mission. So to close, I just, yesterday we had this nice meeting of head of agencies on the monitoring of carbon emissions. This is a fantastic challenge, honestly. Not only because you don't observe emissions, you observe CO2 and a number of other things. So you need to combine models, observations. Sampling in time and space is really challenging. You need also to improve the existing inventories, and a lot of high-resolution imagery can be used for that purpose. You shall not neglect that at certain times of the year you have fast uptake from the vegetation and the ocean. So we have an undetermined, it's a bit like meteorology. If you were told, okay, observation is enough. No, you need to combine everything into an information system. We need to make best use of all we have and all what will be available. And certainly all the cooperation models I have presented to you are relevant, and we need to consider them to see how we move forward. Thank you very much.